Well, welcome again to A-Level Physics. This is Furen International School, and I'm Patrick Van Twest. Thank you for having me on your device. We're into Topic 2, Kinematics, and this is the third lesson. Today, the key words for you to know very well are the following: two-dimensional, perpendicular, projectile motion, parabola, independently, visualize, and range. So there's some big words there, so try to know those well. Okay, do you remember last lesson what we did? And can you remember that we looked at writing equations that help us describe motion very completely and very succinctly when we have uniform acceleration? Okay, so could you close your eyes and remember these four equations? You could try it, okay? So these are what we learned last lesson, and we saw especially that we can apply these formula when we have straight line motion. So we looked at vertical motion, horizontal motion, when the acceleration is constant. But I left you with a question. I asked you what could we do, or how would we approach things if we had now two directions, two perpendicular directions, like vertical and horizontal, if we had motion in those two directions going on at the same time. So if you look at this picture here, there's a ball moving vertically up and down, but it's also moving horizontally. Okay, how do scientists handle this? Well, we're going to explore that today. And I think the best way to explore it is first to just study, just to watch, okay? That's what scientists do. We like to observe. So watch this projectile motion. This is called projectile, something that's being projected or thrown, or in this case, a cannon is firing a ball. And I want you to watch the path of the projectile. And on the path of the projectile, you'll see the velocity in the horizontal or x direction is staying the same. So that arrow, horizontal arrow, represents the size of the horizontal velocity. It's staying the same, but can you see what's happening to the vertical? Okay, the vertical velocity, or Vy, is increasing. Okay, so watch the numbers here and watch the arrow there, and then together we have both of those motions happening at the same time. So what we can say is horizontally we have zero acceleration if there's no air resistance. Okay, so we have constant velocity happening horizontally, but constant acceleration, and that acceleration being 9.8 meters per second squared, or in this graphic it's about 10 meters per second squared, happening at the same time. So what do we do? Okay, I'm going to give you a question to think about. Okay, so I've got two balls here, a red and a blue one. So what do you think would happen if I was to just drop the blue ball, but at the same time I drop the blue ball, I project the red ball horizontally? Okay, so I drop the blue ball, at the same time I project the red ball horizontally. Which ball would hit the ground first? Which ball would hit the ground first? Well, let's see. Okay, we're going to have a look now. I don't have blue and red, but I have yellow and pink shown here. So the pink ball is just dropped vertically, but the yellow ball is dropped vertically, and at the same time it has some horizontal velocity. So can you see what would happen? Which ball would hit the ground first? Can you see? That's right. They actually both hit the ground at the same time. And why that is because you can see here the yellow ball is following the same vertical motion. So it's in the same position as the pink ball vertically. It's just that its horizontal position is changing. Okay, now this is a key thing for analyzing motion in two dimensions, is that what we can do then, this means that we can separate the vertical and horizontal motion because they're 90 degrees to each other. Okay, so because of that, we can look at each one, what we say, independently of the other, and then we can combine those two at the end, as we'll see now. Okay, so here's the question I left you with last lesson. There's a plane flying along, it drops an object, and that object is moving horizontally at the start of its motion, and then it's also falling vertically. Okay, and on this graph here, you can see a graph drawn there. It's shown the path of that projectile, the path. Okay, so what we can do here is we can analyze the horizontal motion separately and the vertical motion separately and then add them back together. So let's see how we would do that. So on this slide, you'll see, if you look at the top of this graph, I've plotted the position horizontally of that projectile each second. So it might be 1, 2, 3, 4 seconds. And you can see it's moving the same distance horizontally, no air resistance, moving the same distance each second. But vertically, can you see? Vertically, it's getting further apart each second. It's accelerating. So if I want to work out where it is after 1 second, I just figure out where it is horizontally, I see where it is vertically, and then I combine them and see that's where it is after 1 second. After 2 seconds, it's here horizontally, sorry, it's here vertically, it's here horizontally, so there it is. 3 seconds, it's there. 4 seconds, it's there, etc. So this is a very powerful tool, separating the horizontal and vertical, what we say, components of the motion, and then combining them back together. Now, let's combine that with our equations, and then we have something very, very powerful for analyzing what we call projectile motion. And this all assumes there's no air resistance. So if you want to know what happens when there's air resistance, just wait a while. We'll get to that in the next topic, actually. Okay, so if you remember from last lesson, we had these equations for linear motion or straight line motion. So if we have a horizontal straight line and a vertical straight line, both happening at the same time, and like we said, if we have constant velocity in the horizontal direction, that means in all these equations here, the acceleration is 0. So if you put a equals 0 into these equations, especially if you put them into the displacement equations, you get a very simple result. You get the displacement horizontally is just the speed, the initial speed, multiplied by the time. And then vertically, if you put a constant acceleration of negative g, the gravitational acceleration, you can put that into all those equations also. Okay, and the key thing, the one thing in common between the two motions, can you see what it is? Or can you guess what it is? That's right, the time is common. Okay, so it's a common time. So let's do some actual problems, examples, to see how you would combine these equations and use them in 2 dimensions. Okay, so read through this question, and I'll help you at the start of it, but I'd like you to try to finish it. Okay, so I'll help read it with you. A stone is thrown from the top of a vertical cliff, 45 meters above level ground, and it has an initial velocity of 15 meters per second, horizontal direction. Okay, so that's going to be important. How long does it take to reach the ground, and how far does it end up from the base of the cliff when it reaches the ground? Now, the first thing I would suggest with all these is to visualize the situation. That's to try to picture the situation, to see it, and then to write down all the quantities you know from the question, so all the numbers and values in the question, to put them on your diagram, both horizontally and vertically. This takes a bit of time, but I think it's well worth it, as hopefully you'll see as we go through. So we have the same question here. I'm just going to try to visualize now, and it's key that I assume no air resistance. Okay, so I see here in the question it talks about the horizontal direction. Initial velocity is only horizontal, so this means this is also a key component here. The projection is horizontal only. That means initially there's no vertical velocity at time 0. Okay, that's going to be important. So vertically, I could write the initial velocity vertically is 0, but the acceleration is the acceleration of free fall. Now horizontally, I know the horizontal speed just stays the same, no acceleration. Okay, now when I do that, then horizontally I can describe the displacement by just saying it's the speed multiplied by time, and vertically I can describe the displacement or the height. If I say height is 0 at the top, then the height will be negative half gt squared. Okay, so now let's go and put those numbers in because I want to find the time when it reaches the ground. Now, do you remember we said that it's 45 meters in the air? So when the vertical displacement is 45 meters below the initial height, that's the time at which the stone will hit the ground. So if we just put those numbers in here, so 45, and then t is the unknown, g is minus 9.8. So you see the negative numbers cancel there, and then you end up with a positive t squared. So t is 3 seconds. So remember, the time is also the same with horizontally. That's the one thing in common. So after 3 seconds, if it takes 3 seconds for that object to hit the ground, how far would it have gone? Well, horizontally, it's just traveling at 12 meters per second. So multiplied by 3 seconds, you get 36 meters. Okay, so it's quite a bit of mathematics and quite a bit of problem solving to get there. But I think if you go through all the steps, you'll find it's not too difficult. You can do it. Okay, so on to the next question. I've just added an additional question here to show you also that we can also find the stone's velocity at any point in its motion. And just for an example, what would the stone's velocity be when it hits the ground? Okay, so the same thing we can do. Instead of looking at displacements, we can look at velocities, both horizontally and then vertically also. So horizontally, the velocity is just constant, so I could draw that, try to visualize it, 12 meters per second, constant. Now vertically, what would the velocity be when it hits the ground? You can see that it's changing, yeah? The vertical velocity is changing with time according to this equation. Do you remember v equals u plus at? So if I put in the values, remember the initial velocity vertically was 0 because it was all horizontal, the initial speed, and then I'm taking away 9.8 meters per second every second times 3 seconds. That was the time when it hit the ground. So if I calculate that, I get a vertical velocity of 29.4 meters per second downwards. So now all I have to do is add these two vectors, that's right. So can you remember how to add vectors? We've got 12 meters per second horizontally, 29.4 meters per second vertically. If I want to add them, this is good revision. Do you remember what to do? Remember, we go tail to head of our vectors. We mark the start position, we mark the finish position, and there we go. The resultant velocity, or the total, is just the vector addition of those two vectors. So if I wanted to calculate the size of v, can you see what I've got? It's a right-angled triangle. Pythagoras comes to mind. So Pythagoras' theorem says this. So the velocity is then the square root of 12 squared plus 29.4 squared, or 32 meters per second. And the angle you can calculate using your trigonometry, okay, that you study in maths. So there it is, tan theta is the opposite over the adjacent, or 29.4 over 12. If you take the inverse tan, then you get 68 degrees. So you've calculated the velocity in size and in direction. Okay, so what we looked at there was projecting horizontally, but of course, normally, very often in life, we project things at an angle. Okay, so if we want to get more general, what would happen if we throw something, like in this slide, at an angle to the horizontal? Can we describe the motion? Well, yes, we can. We can describe it completely with those formula. If we assume there's no air resistance, it's just a little bit more involved. So let's go through the process. So horizontally, what we could say is the initial velocity horizontally is the initial velocity u multiplied by cos of the angle that we throw it at. So if the angle was alpha, it would be u times cos of alpha. Okay, then to get the displacement, it's just the constant speed horizontally multiplied by the time. So I'm using this formula here. Remember this one? S equals ut plus half at squared. And then vertically, I'm using that same formula. Ut becomes u times sine of theta. So that's the vertical component, is the sine of the angle. And then I'm taking away half gt squared because we've got vertical acceleration happening due to free fall. So let's look at an actual problem with this one. Okay, this is a good question to try. This time I want you to pause the video for yourself and try to visualize this question, maybe draw it out, mark on the information, and then see how far does the ball go if the ground is level. Okay, try to wrestle through this question, see if you can get an answer, and then come back and look at how we did it. So what I again say is that the key is to visualize the situation and write down all the things you know, both horizontally and vertically. So here's what I did. Okay, I drew maybe the path that would take if I project at an angle. Now also just a small note here, I'm assuming that we start at the ground, okay? In reality, we might start a bit above the ground when we throw things, but we could just add that on, that extra height. It just makes things a bit simpler if we start on the actual ground level, okay? Then I've marked on everything this question tells me. I've marked on the initial velocity of 18 meters per second at that angle of 45 degrees. And then I've just marked here the vertical displacement as SV and the horizontal displacement as SH. And those things are changing over time, okay? And this formula is very useful, this equation. Okay, so horizontally, then what we have, if we just put the values in, 18 times cos 45 times t, and vertically we have 18 sine 45 times t, and then also taking away this factor due to the acceleration. Now the question asked us, how far does the ball go? Right, now can you see the key for working out how far the ball goes is by knowing that when it hits the ground, its vertical displacement is 0. That's right, it's come back to the ground. So it's a bit like a ball going up and then down vertically. When it gets back to where it started, its displacement vertically is 0. But in that time, it's moved horizontally. Okay, so let's see what the equations tell us. The vertical motion, if we put 0 into our equation that we had, 18t times sine 45 minus half 9.8 times t squared, that equals 0. We can calculate what time it took for the ball to reach the ground. Okay, so 12.7 t minus 4.9 t squared equals 0. Do a bit of mathematics, take t out the front of your bracket. 12.7 minus 4.9 t times t equals 0. That means either t must be 0, one of these two factors have to be 0, or 12.7 minus 4.9 t equals 0. So either t is 2.6 or t is 0. Well, t equals 0 is just at the very start. Okay, that's when the ball was here at time 0 on the ground, and then another 2.6 seconds later, the ball was there on the ground. So this is the one we want for how far it's gone. So now I know that t equals 2.6. I can use that in my horizontal equation. Can you see? So if I just put t equals 2.6 here, I'm getting very close to a final answer. 18 times cos 45 is the horizontal projection of the velocity times 2.6 seconds, 33 meters. Wow, that was quite a sum, quite a calculation, but I've found my distance that the ball has traveled. Okay, so the range in this picture here is called r, is defined as the distance from the point of projection, or from the starting point, to the point at which the particle or the object reaches the ground again. So you can see in this picture, all we need to know is the speed at which we project and the angle, and we can calculate a value for the range using this. U squared equals sine of 2 times alpha divided by g, where alpha is the angle of projection. Now this assumes there's no air resistance. Okay, and this could be for a javelin or a discus or any sort of projectile. So a very good question to ask you is, if I were throwing an object or like a javelin, what would be the best angle to throw it at for my speed? What would be the best angle to get as far as possible? Okay, can you see in this formula what value of alpha would give you the biggest value of sine 2 alpha? Right, here's some options. If you look at this graphic here to the side, if there's no air resistance, then we see that if you go for 80 degrees, it doesn't go too far. If you go for 10 degrees, it doesn't go too far. The range is small. 60 degrees or 30 degrees, the range is getting bigger, but the best is, that's right, 45 degrees, right? Assuming that there's no air resistance, then 45 degrees is the best angle to get the furthest range, because 2 times 40 degrees is 90 and sine of 90 is 1. Okay, here's a final question. Quite a good question to go through. So just read through this one and you've got 4 choices. See which one you would choose. So maybe press pause and try this one. Okay, here we go. So a stone is thrown upward and follows a curved path, as we see there in that picture. Air resistance is negligible, that's important. So why does the path have this shape? And do you remember what we call the shape? That's right, it's a parabola. Okay, why does it have a shape like this? Which one of these answers would you go for? Okay, now the key for me is during the flight, the only acceleration is vertically down. As we've seen in all the examples today, the only acceleration we've looked at is down. So these other answers that talk about a horizontal acceleration or an upwards acceleration, they just won't apply in this situation because the only force acting on the stone is its weight. Okay, that's why as soon as you let it go, that is, okay? So after the stone is released, the only force acting, there's no air resistance, is weight. And that leads us to our next topic. We're going to be looking at how forces affect motion. Okay, so this is a good place to end this lesson, and I hope you'll be keen to join us for the next one. We'll just look at what we've uncovered today. So a quick summary. Today we've seen that motion in 2 perpendicular directions with no air resistance we can analyze by treating displacement and velocity in each direction independently. We've also seen that we can combine then each direction to give the overall displacement or the overall velocity. So it's a case of looking independently and then combining. And then we looked at particular examples of projectiles. Okay, we started by looking at a horizontal projectile, and then we looked at projecting at an angle. And we saw that those equations could help us solve those problems. The key tip in those problems was for me to visualize the situation and then to write down the things you do know. And finally, we looked at the meaning of range, that it's a distance traveled by projectiles, and we saw how you could calculate it also. So I hope you enjoyed this lesson and learnt many things. So until next time, the heights might be scary, but we hope you will rise above the ordinary.
Welcome to Furen International School, Singapore. We have international staff with global work experience and students with the highest academic achievements. Our modern city campus is equipped with state-of-the-art learning facilities and a practical science laboratory. And our focus is on student development to mold them into a global citizen. Singapore, the vibrant, first world economy of Southeast Asia, is the perfect home for an advanced learning center. We are located just off the city's upscale Orchard Road. We lead the way in preparing entry into world-class universities. FIS students with strong grades enter universities from all over the world. Many will enter a global top 100 university. Our brightest will enter Oxford and Cambridge and other G5 institutions. Not forgetting Singapore's best universities. Our students have scores top in the world grades in maths and other subjects. They are encouraged to debate in the Model United Nations and are groomed to be leaders of tomorrow.
如果一定说辅仁对孩子们做了一些特别的地方的话，那就是老师们对教学的认真和对孩子们的关爱。也有孩子说，我很难想象一个老师，我很晚了，有时候11点钟发信息给老师，老师也会及时的回复我的信息，这是他们在辅仁学习当中感觉印象深刻的一点。所以呢，如果说辅仁在某一方面能做得相对成功的话，这是师生共同努力 丽的结果。所以在此，我非常感谢孩子们为自己的未来肯拼搏，也感谢家长给予我们的信任，也感谢代理呢给予我们的支持，使得我们这样普普通通的学校，因为这些有理想的孩子的云集，有努力的一群对教育有热忱的老师环绕在孩子们身边，使得孩子们的升学有这样还算令人满意的结果。所以在此我表示深深的感谢，谢谢大家。
Our students score very high marks in the core sciences and maths. Many go on to careers in science, computing, and engineering with a new medical pathway now on offer.
Our students are very fortunate to have the Cambridge International Examination as their pathway to university success. Our students have wonderful, dedicated teachers who lead them and guide them and help them at every step of the way in their journey. Our school is a centre of innovation. It is a progressive environment where we give all of our students every opportunity to succeed.
Middle school students also engage in the arts, robotics, and swimming, and a range of activities to stimulate their minds and keep bodies fit. Student welfare is important to us, teachers and staff counsel students and understand their needs. Our school is also a centre for IELTS study and SATs examinations. High school students are encouraged to focus on their academics in 18, 24 or 36-month programs. Students at FIS make good friends and will learn to bond at our hosted facility, called JJ's. Learning independence is a positive step in a Furen student's life. Singapore is a safe and convenient destination for students from everywhere, whose desire is to make their mark on the world. Join us to take the next step in an exciting and wonderful future. Start your pathway to a world-class university at a world-class preparatory school. We look forward to seeing you soon.